Welcome to The Explainer. This is where we break down some pretty big topics into clear, concise presentations.
So, what do a camera flash, a computer keyboard, and your phone's touchscreen all have in common? I know, it sounds like the start of some kind of tech riddle, right? I mean, these things seem totally unrelated. But believe it or not, they all rely on one tiny but incredibly powerful little component that's doing all the heavy lifting behind the scenes.
And that little component? It's the capacitor. Now, you can kind of think of it like a super tiny battery, but one that can charge up and then unleash all its power in a split second. And that's its superpower, really. This ability to store energy and then release it in an instant. It's the secret ingredient that makes your camera flash work, and it's even what makes the touchscreen on your phone, well, touch sensitive.
So today, we're going to do a deep dive into this amazing little device. We'll kick things off with a really simple analogy, then we'll get into the actual physics, see how they behave in circuits, and then, this is the fun part, we'll connect it all back to how we actually use that energy in the real world.
All right, let's get into it. What is a capacitor? Now, to really get a handle on this, we're not going to start by throwing a bunch of confusing formulas at you. No. We're going to start with a really simple analogy that I promise will make the whole concept just click.
Okay, I want you to picture a big water tank. You can fill it all the way to the top, right? And as you do, you're storing potential energy. Then, imagine opening a huge valve at the bottom. Whoosh! All that water comes rushing out in one massive, instantaneous burst. Well, a capacitor does exactly that, but instead of water, it's doing it with electric charge.
Okay, so that's the analogy. Now let's get a little more technical. At its heart, a capacitor is actually incredibly simple. I mean, it's really just two conductive plates. Think of them like two sheets of metal, and they're separated by a little gap, an insulator. That gap could literally just be air.
And what you're seeing here, this is the classic design for one. So when you connect a battery, these plates start acting like magnets for electric charge. You get positive charge building up on one plate, and an equal amount of negative charge gathers right across from it on the other plate. And the basic rule of thumb here is super simple. The bigger the plates, and the closer you stick them together, the more charge you can pack in there.
All right, so we've got the basic idea of what a capacitor is, but how do we actually measure its ability to store all that charge? Well, it all boils down to one simple, really elegant formula.
And this is it, the golden rule. Q equals C times V. This is the whole ballgame right here. What it's telling us is that the amount of charge, that's the Q, that a capacitor can hold is directly tied to the voltage, the V that you apply to it. So you pump in more voltage, you're going to store more charge. It's really that straightforward.
So what about that C in the middle? Well, that C stands for capacitance. And that's just a number that tells you how good a capacitor is at its job, how well it holds charge. A bigger capacitance means it can store more charge for a given voltage. And here's the really cool part. The capacitance, that C value, is totally determined by the capacitor's physical design. You know, the size of its plates, how far apart they are. It has nothing to do with the voltage you're applying.
Okay, so that's how a single capacitor works. Pretty cool. But what happens when you need a little more storage, or maybe a little less, than what a single standard capacitor gives you? Well, that's when you start connecting them together in circuits. I mean, think about it. In the real world of electronics, you can't just go to the store and find a capacitor with the exact capacitance you need for every single project. It just doesn't work that way. So what do? You get clever. You combine them.
So one way you can do this is by linking them up end to end, kind of like a chain. We call this a series circuit. And you can think of it like a one-way street for the charge. The exact same amount of charge has to pass through the first capacitor, then the second, then the third, every single one in that chain.
And this is where things get really interesting. You can see the big difference between connecting them in series versus what we call parallel. When you put them in parallel, it's easy. You just add up their capacitances. You get a bigger total storage tank. But here's the weird part. When you connect them in series, the total capacitance actually decreases. It ends up being even less than the smallest capacitor you have in the chain. It sounds kind of backwards, I know, but it's an incredibly handy trick for when you need to get just the right value for a specific job, like, say, fine-tuning a radio circuit.
Okay, so we know we can get more storage by hooking up capacitors in parallel. That's one tool in our toolbox. But what if you want to get more out of just a single capacitor? Is there a way to supercharge it?
Well, it turns out the secret to a supercharged capacitor isn't about making the metal plates bigger. Nope. The secret is in the empty space between the plates.
If you fill that gap with a certain kind of material, you can dramatically, and I mean dramatically, increase how much charge it can hold. This special stuff is called a dielectric. And a good way to picture what's going on inside is to think of its molecules as a huge crowd of tiny, confused compass needles. Normally, they're just all over the place, pointing in totally random directions. But the second you slide that dielectric material between the charge plates of the capacitor, something pretty amazing happens. The electric field from the plates forces all of those tiny little molecules to snap into perfect alignment. And when they do that, they create their own small internal electric field that actually pushes back against the main one.
And here's why that matters. This is the key takeaway. The dielectrode's own little opposing field actually makes it easier to pack more charge onto the capacitor's plates. So what does that mean? It means we can get way more storage without having to crank up the voltage. And we measure this boost with a number we call the dielectric constant, or kappa. The higher that number, the bigger the boost you get.
All right, so we've been talking a lot about storing charge, storing charge, storing charge. But so what? What's the point? Well, the real magic begins when we actually use that stored charge, when we turn it into useful energy. This is how we get from all these physics principles to something like a blinding camera flash. See, all the work you do to cram charge onto those plates doesn't just disappear. It gets stored as potential energy, right there in the electric field between the plates. And this formula, U equals 1/2 CV squared, tells us exactly how much energy we've got stored up ready to go. It all comes down to the capacitance and the square of the voltage.
Okay, so to really drive home how much our circuit choices matter, let's run through a quick example. Let's say we have two completely identical capacitors. If we connect them to the same battery, the same voltage source, which setup is going to store more energy? Putting them in series or putting them in parallel?
Well, the math here is actually pretty simple. Like we saw a few minutes ago, when you put two identical capacitors in series, your total capacitance gets cut in half. But when you put them in parallel, you double it. And right there, that's already a massive difference. So what does that mean for our energy storage? Well, since the energy depends on the capacitance, the parallel circuit holds 4 times more energy than the series one. A 1-to-4 ratio. I mean, think about that. Just by changing how you wire two little components, you can get 4 times the energy out of them. That is a total game changer in electronics, and it really shows you why these design decisions are so important. And really, that's the capacitor in a nutshell. We started with a simple water tank, and we ended up with the pretty wild rules of electric fields and dielectrics. It just goes to show you how this one tiny, simple component plays such a huge role in the tech we use every single day. It's a great reminder that even the smallest building blocks of our modern world are just packed with absolutely fascinating science.
Please like, share, and subscribe for appreciation and such more learning friends.